Broadcast is now starting. All attendees are in listen-only mode.
Good morning, ladies and gentlemen, and please welcome to Dormer Pramet online training. This is our fourth session this year, and today we will be more technical. We will be talking about chip thinning. This subject actually needs some more time to digest. So what we have done prior to this presentation, we have actually provided you with handouts. You will have a copy of this presentation and some useful formulas in handouts. So just navigate to your webinar panel. There is a section named Handout, and there are two PDFs. So please download those PDFs. If you are not able to do it for any reason, just drop us an email at the end of the show at cs@dormerprime.com, and we will provide you that later, or it will be available on our website. And as usually, we will answer all your questions at the end. So please feel free to write your question during the time, during the presentation, and we'll come back to it at the end. So now please sit down, relax, and enjoy some chip thinning training. Jesus?
Thank you, Martin. Appreciate the introduction there. Welcome, everyone. Appreciate your time and effort on joining us in this webinar, which has to deal with high feed milling and so-called chip thinning. So in keeping with tradition, we know that Dormer Pramet is always looking at safety as number one, and we always try to keep everyone in a safe way in the environment and anything else related to that. So let's look at chip thickness. Chip thinning is a phenomenon that occurs with varying radial depths of cut and relates to chip thickness and feed per tooth, which is referred to as IPT or chip load. So what is chip thickness? Chip thickness refers to the actual thickness of each chip cut by a tool measured at its largest cross section. So when we use the term feed rate, we mean the speed with which the tool travels in time. We use the term feed rate because that is what is programmed into the machine controller. But more important, that the measurements of the chip load is measured in FC and the chip thickness in TC. The chip load is the feed per tooth, and the chip thickness is basically the cross section of a chip. When a chip is formed, it starts to curl, as you can see from this picture here on the left, related over to the right here. And so the surface of the chip inside the curl is kind of rough. That is because the primary shear zone layers of the workpiece are being pushed forward and upward, creating small waves on the surface of the inside of the curl. The side of the chip that shears along the cutting edge should be smooth and shiny. The thickness of the chip is partly a result of this combination of spindle speed and feed rate. So when you change one of these two, the chip thickness will change. When you change both in the same way relative to each other, the chip thickness will stay the same. But more important is the fact that the chip thickness tells us how hard the tool is working. Operators typically like to talk about the chip thickness. Sales engineers generally talk about chip load or feed per tooth. We need to realize that they are not the same. So when you change over to a cutter with more flutes, you have to feed it faster to maintain a particular chip thickness. Since each tooth is going to take a cut at every rotation, a tooth has only a fraction of a rotation in which to cut a chip that reaches the required chip thickness. During the time it takes to rotate and the next tooth starts cutting, the tool has to have moved far enough to shave off a chip that is thick enough, which means that the tools with more flutes can be fed faster. A 4-flute end mill can be fed twice as fast as a 2-flute, all things being equal. It's important to manage the chip load to maintain the right chip thickness. If you don't, you could end up with catastrophic failure. So how does chip thinning occur? First of all, chip thinning adjustments can only be applied when the radial depth of cut is less than 50% of the cutter diameter. A cutter with 50% step over or engagement equates to having the chip thickness and the feed per tooth equal to each other. Each tooth engages the workpiece at a right angle, allowing for the most effective cutting action. Once the radial depth of cut falls below 50% of the cutter diameter, as you see on the right-hand side here, and the engagement on the left is 50% from there to the bottom here, and it's definitely less on the right-hand side, the maximum chip thickness decreases, in turn changing the ideal cutting conditions of the application. This can lead to poor part finish, inefficient cycle times, and premature tool wear. The goal is to produce a constant chip thickness by properly adjusting the feed rate when changing at different radial depths of cut. In this picture, in order to keep a constant chip thickness, we adjusted the feed rate for varying depth of cuts. We can use the formula shown up above. The D is equal to tool diameter, IPT is the feed rate, CT is the chip thickness that you would like to use, RDOC is the radial depth of cut. For the chip thickness, we can use the value of IPT at the recommended value at 50% step over, as you see here on the left-hand side of the picture. This formula will give you an adjusted feed rate in order to maintain a constant maximum chip thickness. As you can see in the picture on the right, our step over is less than 50%, or basically at 12.7, as you can see here in the arrows here. But the formula allows for increased IPT, thus giving us the same maximum chip thickness. There are two different definitions for the chip thickness. There's HM, which is the mean or average chip thickness, and there's Hmax or HEX, which is the maximum chip thickness. It is important to know what the chip thickness is because together with the depth of cut, or the AP, it indicates what the chip load is, and the chip load equals the amount of stress you apply to the insert or cutting tool edge. Although the HM is most used as it will give you the average of forces applied, we recommend to calculate and work with the Hmax, as this is the value for maximum load that the tool would see. Now, we don't directly mention the Hmax values as such in our catalogs. However, the FZ values in the application range of where you would find our insert geometries equates to our Hmax. As mentioned, FZ starts out being equal to the Hmax. In the picture above, the red line shows the maximum chip thickness or maximum load, and it's reached at 50% radial immersion with a chip thickness at 1 millimeter. The green line shows the average chip thickness, still at 50% radial immersion, but the chip thickness is now at 0.64 instead of 1 millimeter thick. This chip thickness continues to increase up to around 80–85% until the maximum chip thickness, which peaks at 50%. The dotted blue line shows the radial immersion at every 5 percentage points increase. The two formulas to the left allow you to calculate either the Hmax, as the one in the red up above, or the HM, chip thickness, the green below. Here, the graph on the left shows the maximum chip thickness. You can replace the FZ and read it as Hmax, which is down here in the lower left-hand corner. The FZ on the graph on the right can also be interpreted as the Hmax, which in this case is 0.02 to 0.098. You can see these types of graphs in the technical section of our catalog with descriptions of the chip breakers as well. So let's try to simplify a little with this picture. The blue chip represents a very shallow cut, and the red chip a deeper cut. Note how thin the blue chip is at its widest compared to the red chip from a deeper cut. We're talking about the width up here on the left or the width down here on the blue section. You can see the chip gets thicker all the way to the point where we've buried the cutter to half of its diameter. That's the thickest point. And because the blue chip shows a more shallow cut, you can speed up the feed rate just to get the same chip load as you had on the heavier cut in the red section above. Chip thinning simply answers the question, how much faster do we have to go so the maximum width of the blue chip is the recommended chip load that we wish to have? So chip thickness is reduced relative to feed per tooth by two different techniques. There's cutter radial immersion, and there's the insert entry angle. Let's look at the first one, which is radial immersion. Table feed is calculated using feed per tooth. It's important to consider the chip thickness before deciding the feed per tooth in order to optimize the process that you will be running. This calculation is used to establish the relationship between the maximum chip thickness actually seen by the insert cutting edge and the machine tool feed per tooth at the center of the cutter. So in this example, just because you may have programmed a feed rate of 0.006, but what the tool sees is actually a chip thickness of 0.004, as you see in this example up above. We want the HEX to be equal to the feed rate, and we want 0.006. From our example, we are given in red the cutter diameter and the radial depth of cut engagement up above. We've calculated the RPM, which is the surface footage of 840 times 3.82, which is a constant, divided by the cutter diameter of 4 inches, and that gives us 800 RPM. Then you take the 800 RPM and multiply it by 0.006, which is the number of teeth, or the IPT, I should say, and then that will give us 4.8, and then multiply by 6 teeth, and that gives us what the feed controller would like to see, in this case 28.8 inches per minute. So the formula reads cutter diameter of 4 inches divided by the cutter engagement of 750, which is down here, multiplied by 0.5. Then this is divided by the square root of 4 divided by 0.75 minus 1. This equals 1.28. Then you multiply the chip thickness of 0.006, which in turn gives you a new feed rate of 0.0077. So we've gone from 0.006 to 0.0077. The main thing here is to know that we started with a feed of 0.006, and by using the formula, we are able to increase to 0.0077. So with our new program centerline feed now at 0.0077, our chip thickness now equals what we wanted, which is 0.006 up here on the right-hand corner. So our new table feed is calculated using feed per tooth. It is important to consider the chip thickness before deciding the feed per tooth to optimize, as I said, the process. Because we took advantage of the radial immersion, we were able to increase our feed rate to 36.96 from 28.8. Now let's look at the second way to achieve chip thinning, which is the KR, or the entry angle of the tool. You can see here several milling concepts with different lead angles. Each of these concepts are designed to perform specific tasks. For instance, a 90-degree cutter is well suited to create a shoulder. A 45-degree cutter is not. A 90-degree cutter can easily be used as a face mill, but it won't be as productive or cost-effective as using a 45-degree cutter. Buttons are many times used in more difficult materials. Regardless of the material, round inserts give the highest total material removed due to higher feed rate capabilities. The engagement or introduction of the insert to the material is very important. One of the things it tells us is how much force is generated upon the axis of the machine. In the above picture, the 45-degree cutter on the right has a force evenly distributed axially and radially. The 90-degree cutter on the left has more force upon the radial axis, as you can see in these two arrows to the left, which in turn can lead to faster tool wear and issues such as vibration, to just name a few. So looking at the 90-degree cutter, it has high radial and low axial forces. The majority of forces will go across the top of the component, poor on long overhangs, creating vibration. Good for thin wall components to prevent vibration with the box castings, and consider the radius size and the depth of cut. If the AP is less than the radius, then it'll function more like a round insert. When we're looking at a 45-degree cutter, it has equal axial and radial forces. Half the forces will go across the top and the other half will go into the spindle, as you can see by the arrows here on the right-hand side. When compared to 90-degree, there are less radial forces to cause deflection, more axial up into the spindle. It's good on long overhangs, good on poor or weak spindles. In the case of a 19-degree cutter, nearly all the forces are axial or going straight up into the spindle. For rigid components, all forces are directly into the spindle. It's excellent for weak or poor spindles. On a round insert, the direction of the cutting forces will change depending on the depth of cut. If the AP or depth of cut is 25% of the IC or the inscribed circle, then the forces would equate to those of a 45-degree cutter. As the AP or the depth of cut becomes less, then this equates to lower radial forces but higher axial forces, which is what we like to see, the forces going up into the spindle. So overall, when using a round insert, we can control the stability of the process by reducing the depth of cut. So looking at chip profile, it is one of the factors that influences the cutting edge stress and cutting force magnitude. These cutters above show examples of compensation for each specific cutters. These are constant numbers that are given. These values are associated, in this case, a 90-degree has a constant of 1.0. A 45-degree has a compensation constant of 1.41. A 19-degree down here has a constant of 3.072. And the last one down here, a 10-degree, has a constant of 5.76. So now we can review the formula using both radial and axial chip compensation. So our factor for a 45-degree cutter, as we just seen in the previous page, the constant was 1.4. We start out with a table feet of 28.8 inches per minute. Then by using our radial immersion calculation, we were able to increase our inches per minute up to 36.96 inches per minute. We recalculate using 0.0077 by our 45-degree constant of 1.4, which now gives us a 0.011 IPT. Then we finish the formula, multiplied by 800 RPM, then by 6 teeth. And so as you can see, by using the entry angle constants, we are now able to increase the inches per minute up to 52.8 inches per minute. So now you have increased productivity by 83%. So tell me, who would not want this kind of increase? This is meant to help you at the spindle when running our cutters and give you the ability to increase the end user's productivity. In this picture, the red area in the table above illustrates the resulting average chip thickness, or the HM, achieved when the radial engagement of the cutter is reduced and the feed per tooth is not increased. When using 50% to 100% of the cutter diameter, the feed rate of 0.006 will produce a 0.0042 HM required by the edge prep of this tool for chip thickness. As you can see here, 100 or 50%, your chip thickness is 0.0042. As the percent of D1 engagement falls below 50%, the average chip thickness thins out to less than the thickness of a piece of paper. So to achieve the 0.0042 average chip thickness that we'd like to see, that's required, the feed per tooth or flute must be increased as the percent of D1 engagement is reduced. The main purpose or benefit of chip thinning adjustments is to get the most out of your tool. Keeping the chip thickness constant ensures that a tool is doing as much work as it can within a given cut. We also reduce the rubbing from material due to no chip thinning adjustment, increase material removal rates, and improve tool life. So part of that is high feed milling is about chip thinning. You must increase your feed rate in order to compensate for the chip thinning effect that is created by the large entry angles of the tool. In maintaining the feed equal to the chip thickness, we are making sure that the chip is thick enough to absorb the heat created by the milling process. Some things to know about high feed milling. It looks, when you're looking at HPM or high productivity machining, it looks at removing as much material as possible in the shortest amount of time. It combines a shallow depth of cut with a large cutting radius and small lead angle, which ensures that cutting forces are axially directed towards the machine spindle. It is highly effective in cavity milling and in the mold and die making. Several things to know in order to make high feed milling successful. Machines must be rigid and capable of high feeds and speeds. The machine and controller must have high-speed machine look-ahead features and high feed rate capabilities. Inserts with lower lead angles produce a thinner chip, which equates to higher feed capabilities and directs cutting forces in the axial direction or into the spindle. Higher lead angles produce a thicker chip, which produces higher radial cutting forces, which can produce vibrations. The insert grade, choosing the correct grade for the material being machined, will allow for tool predictability, which requires less tool changes and produces less scrap. Machining application must be kept in mind if high feed end mills have long overhangs, which you must use specialized anti-vibration tool holders or reduce the cutting speed. Programming must be optimized for the cutter tool path when programmed so that the function can be correctly done and that high feed milling can be achieved. Engaged tools with high feed end mills work better if engaged across the full diameter of the tool and less than half the insert width. They are designed to direct the cutting forces in the axial direction or towards the machine spindle. Engagement of 50 or 60% of the cutter diameter will cause the cutter to push back, thus creating vibrations. Dormer Pramet has a great selection of high feed cutters, suited for die and mold as well as for deep pocket milling. Cutters made for today's technology, incorporating needs such as longer reach, lower cutting forces, smooth cutting for required surface finish, and designed to prevent work hardening. With so many choices, sometimes it's hard to choose the correct cutter. Depending on whether your needs are towards productivity or cross-driven, you can choose, in this case, the SBN 10, double negative cutter for high feed milling, cost-saving, double-sided 4-edged insert, material specific to the M, M&M, and HM as far as geometries. A corner radius protects and enhances the cutting edge durability. The Feed CD, a strong 4-edge insert designed for mold and die applications, designed to direct the cutting forces up to the spindle to enable low depths of cut at very high feed rates. And the Penta HF, a positive but strong 5-edged insert available in many grades for machining a wide range of materials, designed to direct the cutting forces up the spindle to enable low depths of cut at very high feed rates. So some of the benefits of high feed milling is that you have the increased productivity, triple the removal rate compared to conventional methods, improved tool life, lower cutting forces, and decreased workpiece cycle time. Along with the needs for high-speed machining are the programming techniques that will tell the machine controller what to do. CAD/CAM technology is evolving to meet the needs of toolpath strategies for high-speed machining. One of the biggest challenges for CAD/CAM is to create toolpath with small step-overs at very high feed rate. Techniques are being implemented into CAD/CAM to optimize the toolpath and to take advantage of the high-speed machining. Techniques such as remaining stock acknowledgement after roughing, dealing with internal sharp corners, auto reduction of feed in the look-ahead mode, and methods such as trochoidal or slicing. Let's look at these last two. The first is trochoidal milling. Trochoidal milling is an ideal process for applications such as scallops and narrow wide grooves. Trochoidal milling is a 2D method using high-speed milling techniques in a confined space or slot in tough materials such as hardened steel, stainless steel, and heat-resistant superalloys such as Inconel. The tool is programmed with continuous spiral path, controlling the arc of engagement. That keeps the cutting forces low and allows high axial depths of cut. As you can see here, trochoidal milling has spiral graph-like toolpath. It's ideal for milling open pocket slots or grooves, suited for high table feeds. The cutting tool always moves in curved patterns, and it maximizes the highest feed rate throughout the entire process. Slice milling or rest milling. What makes slice milling different from trochoidal is that we progress down to the corner, the engagement increases, so we need to reduce our feeds accordingly. With trochoidal, we kept the feed the same as the tool progressed in, and the arc of engagement remained constant. Like trochoidal, slicing is also used in advanced materials. The first picture is a common method. There's nothing wrong with this method, but it's giving you poor tool life and chatter in the corners. When you hear chirping, it will cost you money. Chirping is vibration, and vibration is loss of tool life. The second picture shows slice milling. Here we're using multiple passes to successfully remove the material using high-speed machining techniques with small radial engagements. The benefits are better tool life, lower cutting forces, and better finish on the component. As you can see here, the picture on the left, the radial engagement is about 150 degrees deeper with the tool, whereas the radial engagement on the picture on the right, it's about 30 degrees, not as deep in the tool. So that's 150 degree engagement versus the 30 degrees. So you'll definitely get better tool life with the one on the right. So that kind of brings us to the end of this. So I hope that this has given you a better insight as to how chip thinning works and how it works hand in hand with the CNC machines and how the CAD/CAM programming comes into play as well. All of these help you to achieve the utmost performance when incorporating high feed milling. And please keep in mind that this presentation is in the handouts, and I believe I also have one in there that shows you the formula broken down step by step and what you should be getting when you use the formula for Hmax. So once again, I thank you for attending, and we'll see if there are any questions that anybody has.
So we have so far received one question from Brandon. So is there any benefit to roll in at the beginning of a milling pass with high feed milling? I would think it would be very minimal.
Now, anytime that you are able to roll into a cut, it is one of the things that's also trying to be incorporated into CAD/CAM programming. The benefit is that the tool is not exactly hitting 90 degrees to 90 degrees face to face. So it is actually going in at an arc and taking a smaller cut before it has full engagement. This saves on your tool life and tool wear, and also on the piece itself is shown as not having as much vibration because you're slowly making that cut into the material itself. So anytime you can roll in, I know it's a little bit more to do the programming of it as compared to straight in. I would always recommend the roll-in method.
And yeah, that was the only question we got so far. So if you have any further questions, please send to cs@dormerpramet.com, or you can actually use the questionnaire at the end to ask the question. Thank you for your attention. It was a pleasure to spending that last half an hour with you, and wish you a great day, and hopefully talking to you again in 4 weeks' time in another session. Thank you, and have a great day.
Thank you, everyone.